So the first two parts of this, we figured out how to write basic Taylor polynomials in Taylor series. Then we figured out how to come up with a formula for writing Taylor polynomials in general. Now we actually get to write the Taylor polynomials for other functions besides 1 over 1 minus x. So just a reminder what our formula looks like. That function f of x equals f of a plus f prime of a x minus a plus f double prime of a x minus a squared over 2 factorial. I'll do one more, and then this will just keep going, right? F triple prime x minus a to the third over 3 factorial, etc., etc. So here's the question, right? This first question is going to look like this. Find the fifth order Taylor polynomial, right? So the fifth order means I want to go up to degree 5. Sometimes the question will say, find the first 5 non-zero terms, and that may or may not be the same thing as a fifth order polynomial. So you got to watch the directions sometimes. This one says find the fifth order Taylor polynomial for, we were talking about the natural log before, so why not try it? F of x equals the natural log of x, and I need a center for this. So centered at a equals 1. Let's use a instead of x. Remember we said natural log would be a terrible one to center at 0 because the natural log of 0 doesn't exist. So this one I'm going to center it at 1. So it says a fifth order Taylor polynomial. And while I'm at it, I'm probably going to find the actual series at the end. That seems like kind of a fun thing to do. And I want the function to be the natural log of x. And I want it centered at a equals 1. All right. So let's try this out. We've got a function, natural log of x. This is the way that I organize it. You're welcome to organize it whatever way makes sense to you, as long as we all come up with the same answer at the end. So if I'm doing a fifth order Taylor polynomial, I know I'm going to need 5 derivatives. So if the original function is the natural log of x, that means the first derivative is 1 over x. Then the second derivative, if I take x to the negative first and derive it, I'm going to get negative x to the negative second. Well, let me write that as negative 1 over x squared, right? That's the equivalent of negative x to the negative second. If I derive it a third time, now if I derive negative x to the negative second, I'm going to get a positive 2. Remember when you drop the power down by 1, it becomes to the negative third. So I get positive 2 over x cubed. And now you can start to see that this is going to alternate. The fourth derivative is going to be negative 6 over x to the fourth, and then your fifth derivative is going to be positive 24 over x to the fifth. All right, then what I do in my next column is I evaluate it at a equals 1, right? So we said we were going to center this at a equals 1, so let's do that. F of a will be the natural log of 1, which is 0. F prime of 1 will be 1 over 1. Oh, okay. F double prime of 1 will be negative 1 over 1. So far, this is kind of boring, but it gets better. The third derivative at 1, so if I put a 1 in down here, I'll get 2 over 1, which is 2. Ah, now this seems more interesting. The fourth derivative evaluated at 1 is negative 6 over 1. And the fifth derivative evaluated at 1 is 24. So I'm going to move the screen up, so you may need to copy those terms down. F of a, or in this case, f of 1, is 0. The next term is negative 1. The next term, positive 1, then negative 1, 2, negative 6, positive 24. All right, you got those written down somewhere. We're going to slide this up, and we're going to start throwing things into our formula. So here's our formula. F of x equals, the first one is f of a. Now what is f of a? F of a in this case is 0, so I'm just going to write it as 0. We'll simplify this. All right, the next term is 1 times x minus a. X minus a in this case will be x minus 1 because a is 1. Then the second derivative, which is negative 1, x minus a to the second over 2 factorial. The next one will be, because this is f of a, f prime, f double prime, the next one will be f triple prime. F triple prime we said was 2. So I get 2 times x minus 1 squared, x minus 1 to the third over 3 factorial. The next coefficient was negative 6. X minus 1 to the fourth over 4 factorial, and then plus 24 x minus 1 to the fifth over 5 factorial. Let's see if we can clean this up a little bit. I claim that the natural log of x is approximately equal to, because it's not exactly equal to, because I stopped at 5 terms. The 0 just drops, right? So I'm left with an x minus 1. Now the next one will be a minus, right, because there's a minus. X minus 1 squared. Maybe I really don't need the factorial next to the 2 on the bottom, so I'll just leave it as 2. Okay. Take a look at this guy over here. This 3 factorial, isn't this 3 times 2 times 1? Well, that 2 over there will cancel that 2 up there, and all of a sudden now, I don't have a factorial anymore. I've got x minus 1 to the third over 3. I'll bet you something similar happens in this next one. 4 factorial is 4 times 3 times 2. Well, that 6 up here cancels both the 3 and the 2 on the bottom, and I end up with a minus x minus 1 to the fourth, and the only thing left on the bottom is a 4. And yep, if you said that that 5 factorial is 5 times 4 times 3 times 2 times 1, that 24 is 4 factorial, so those two things cancel out. And I'm left with a plus x minus 1 to the fifth over 5. Right? So this is a 5th degree or a 5th order Taylor polynomial because it stops at degree 5. It doesn't go any further than that. And that's why I use that approximate sign, because this is not exactly the natural log of x, but it's kind of close to the natural log of x. All right, a couple more things we can do with this. First of all, this is the Taylor polynomial. Okay, suppose you wanted the Taylor series. Well, it's going to involve a summation. I'll bet you it involves an x minus 1 to the n. And here's one reason why you want to simplify it. You realize that in simplified form, it looks a whole lot better than it does in factorial form, because now your exponent is the same as the number on the bottom. Now, we also need it to alternate, so we need a negative 1 either to the n or to the n plus 1. We don't know quite yet. Where do we want to start this series? Well, suppose I start this series at n equals 1. Right, that seems to be a good spot to do it. I want it to be x minus 1 to the first over 1. That's good so far. And I need this guy over here to be a positive. Well, if I just do negative 1 to the n, that's going to be a negative. So let's do negative 1 to the n plus 1. And now it should work. Let's say I try n equals 2, right? The second term will give me a negative 1 to the third, which is negative, x minus 1 to the second over 2 factorial over 2, and then the third one will be over 3 and so forth. So this is the actual series for the natural log of x centered at x equals 1. All right, so how good of a job did we do? What kind of approximation is this? Well, in order to figure this out, I'm going to try graphing it and see what that does. Okay, so let's start a brand new Desmos window. I'm going to slide this over so you could see. I'm going to input my functions. Let's start with y equals the natural log of x, so that you have some reference point for this, right? That's what I'm trying to find the approximation for. So here I'll put in y equals the natural log of x. Okay. My polynomial looks like this. Y equals, as I type more terms, you should see this starting to get better, right? If I just use y equals x minus 1, that's good for a little while, but that's not really that great of an approximation. So now to that we'll subtract x minus 1 squared over 2. Oh, now function goes the other way, but it gets a little bit better. Plus x minus 1 to the third over 3. Okay, so now the function goes in the other direction. It's starting to really hug that original function. Minus x minus 1 to the fourth over 4. And then my last one will be plus x minus 1 to the 5th over 5. Well, by the time I get to that 5th term, look how good of an approximation this is. If I had to make a guess, just looking at that information, I could figure out a couple of things. First of all, I can figure out that this thing is centered at x equals 1. Right? We had said that it was centered at x equals 1, and it looks like that's where everything meets right in the middle. It looks like beyond 2, the graphs start to go apart from each other, and as it approaches 0, it becomes a bad approximation simply because the natural log has an asymptote at 0, and this polynomial doesn't have an asymptote, right? Polynomials just keep on going forever, so it doesn't know that this is a natural log function, and therefore it just keeps going. All right, what could I do with this? Well, eventually we'll get into why on earth would I want to make a Taylor polynomial. You realize that hundreds of years ago, before they had calculators, if you wanted an approximation for, let's say, the natural log of 1.3, you could use a Taylor polynomial, and it'll take you a while to play around with those fractions, but you could get a real good approximation for the natural log of 1.2 or 1.3 by creating a Taylor polynomial centered at 1, and then just throwing in the 1.3 as your x. Same thing if you wanted like a 0.7 or a 0.8. You would end up with negatives, but then some of those negatives would be squared, and you would get positives. All right, so there's a natural log function. Cool. Let's try another one. All right, we just did the natural log. How about the sine of x? Sine of x we'll do a Maclaurin series for. So let's find a Taylor series for sine of x, centered at a equals 0 or at x equals 0, which really means that it's a Maclaurin series. All right, let's go until we get a pattern. So f of x is a sine of x. F prime of x is going to be cosine x, right? Remember derivatives, so the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. And the derivative of negative cosine brings me back to sine. Now, funny thing happens when I go to evaluate it at 0. F of 0 means the sine of 0, which is 0. Okay. F prime of 0 means the cosine of 0, which is 1. Okay. F double prime of 0 means we're back to the negative sine of 0, so negative sine of 0 is still 0. If we evaluate negative cosine of 0, cosine of 0 is 1, now tack on the negative sign, I get negative 1. You can see what's going to happen is when I go back to this sine x over here, is just going to keep repeating 0, 1, 0, negative 1, 0, 1, 0, negative 1. All right, what does that mean? Well, let's say we go to put it in our formula. In this case, the formula will be easy because we don't have to worry about the a's. So we do f of a, which in this case is what? It's sine of 0, which is 0. So there's my f of a. F prime of a, x minus a. Well, a is 0, so x minus 0 is just x. Then f double prime of a, x minus 0 squared over 2 factorial. Then I do f triple prime, x minus 0 to the third over 3 factorial. I do the quadruple prime, which is 0, and then it reverts back to 1, x to the 5th over 5 factorial, and so forth. What you realize is all of the even terms disappear. And so the sine of x will be x, and then minus x to the third over 3 factorial, and then plus x to the 5th over 5 factorial. Now, if somebody asked you for a 5th degree Taylor polynomial, then you've created a 5th degree Taylor polynomial. However, if they asked you for, and sometimes we call this the 5th order Taylor polynomial. However, if they asked you for the first 5 non-zero terms, you haven't given the first 5 non-zero terms because there's only 3, right? There's 3 terms that are not 0. If you wanted to keep going, then you would continue plus x to the 7th over 7 factorial minus x to the 9th over 9 factorial. All right, so I can do this, and then if I want to, I can keep going after that. All right, how do I write the actual series for the sine of x? Well, it's got to involve odd powers. So how do I get an odd power? If I pick, let's say, n can be any number in the world. How do I make n odd? Well, here's another question. How do I make n even? If I multiply 2n, now that number is an even number. Any number you multiply by 2 becomes even. Well, one more than an even number is an odd number. So that's how I represent an odd number. It's got to be one more than an even number. Well, I know how to represent an even number as 2 times something. If I want an odd number, I should add one more to that. So when I create this series, it's going to be sort of a funny looking guy, isn't it? The x's are going to have to be raised to odd powers. That's why I went through how do I find an odd power. It's got to be a 2n plus 1. Well, whatever the odd power is on the top is going to be the factorial that's on the bottom, right? So if we have x to the 5th over here, on the bottom is going to be a 5 factorial. The other thing we need to do is we need to make this thing alternate. So we need either a negative 1 to the n or a negative 1 to the n plus 1, and we should figure out where to start this. Let's not start this at 0. Well, let's see. Actually, if I do start at 0, I get x to the 1st over 1 factorial. Okay, good. Let's start it at 0. And it goes from 0 to infinity. So now, what do I want? I want a positive as the first one. So if I do a negative 1 to the n, that should be good. Negative 1 to the 0 power is 1. X to the 1st over 1 factorial. So my first term is just x. Now try it out for n equals 1, right? N equals 1 would be the next term. I'd get negative 1 x to the 3rd over 3 factorial, and that's what I want. So this is the series that is exactly equal to the sine of x centered at x equals 0. So around 0, this is a good approximation. And when you get into one of your labs, you're going to try to figure out whether this is a good approximation for all values of sine or just for values of sine that are very close to 0. Okay. It might be interesting to find a Taylor polynomial that represents cosine. We've got 2 options when we do that. One of them is we can go back to this process that I did over here and do the same thing for cosine, or we can actually just go, wait a minute, instead of doing f of x and then f prime of x, what if I just called that first term f of x, f prime, f double prime, f triple prime? You realize that the coefficients, instead of going 0, 1, 0, negative 1, will go 1, 0, negative 1, 0, 1, 0, negative 1, 0. The other option that we have is to actually take the Taylor polynomial for sine and derive it. Is that legal? Yes. So you can derive a power series term by term. Right? And you'll see it here, and then you'll see it later on in this chapter. So you can derive a power series term by term. So start with the sine of x as x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial plus x to the 7th over 7 factorial. Oh, sorry, that should be a minus. Okay. And now derive. So the derivative of sine x is cosine x. All right, the derivative of x is 1. When you derive this next term, you realize that 3 out here is going to drop down in front. And so you'll end up with a 3x to the 2nd over 3 factorial. Well, 3 over 3 factorial is really just x to the 2nd over 2 factorial, right? Because you'll have a 3 on the outside. On the bottom, you'll have a 3 times 2 times 1. Well, those 3's will cancel out. You'll just be left with the 2. Same thing's going to carry down over here, right? When you drop the 5 in front, you'll have a 5 on the top and a 5 factorial on the bottom. Well, the 5's will go away, the 4 factorial stays, so you end up with an x to the 4th over 4 factorial. Okay, I got the wrong sign in here again. That should be a minus. So minus plus, the next one will be a minus, x to the 6th over 6 factorial, and so forth. So If you want a series representation for the cosine of x, that's not too bad, right? It's going to be, we said even powers are 2n's, so x to the 2n over 2n factorial. Let's start this guy at 1. Nope, let's start this guy at 0, right? Because we want to start at 0, go to infinity. So x to the 0 power will be 1. 1 factorial is 1, so we're okay on that. If I put a 1 in, I get x squared and a 2 factorial on the bottom. And then the only other thing to check is make sure my signs are right. So if I have negative 1 to the 0 power, that's 1, that's good. Negative 1 to the first is negative 1, that's good also. So that looks like an approximation for the cosine of x. One little connection here that I think is kind of neat. Back when you did graphs of sine and cosine functions, didn't you graph a sine function and the sine function started at 0 and it went up and it went down like that and it kept going, and then over here as well. And we said that this was sine of x. And we said you could take this and you could rotate the graph 180 degrees and you would get exactly the same graph. So a graph with a 180-degree rotation we labeled as an odd function. When we made our Taylor polynomial for sine x, didn't sine x have only odd terms in it? So it turns out that those two things are very much related. An odd function produced odd values, odd exponents, I should say, in our Taylor polynomial. All right, how about cosine of x? Cosine of x had all even powers. So when you take the cosine of x, didn't it dip down on this side? And it dipped down on that side. And this one had reflection symmetry across the y-axis, right? So this had rotation symmetry. This had reflection symmetry across the y-axis. So reflection symmetry across the y-axis was good enough for an even function. And what do you know? Cosine of x has all even powers. All right, I'm going to do one more thing, and then we're going to break it apart into part 4 of this. There's a lot of material in this section. All right, suppose I want the 7th order Maclaurin series for x cosine x. Wow, that sounds funny. I want the 7th order Maclaurin series for x cosine x. And I guess I really could say the Taylor polynomial, because I'm not really writing out the whole series. I'm really writing out just the Taylor polynomial. But the Maclaurin part was my little reminder that I'm really centering this at 0. All right, so I guess I have an option. One of them is I could start with f of x equals x times the cosine of x and derive it 7 times. You realize that's a terrible way to do it because I'm going to end up with product rules every time I derive it. And every time I derive it, I'll introduce another set of product rules. So how do I avoid the heartache of doing that? Well, what if I know that cosine x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. If I were to multiply both sides by x, right, can I do that? Can I multiply this side by x and that side by x? And I end up with what? I end up with x times the cosine of x equals x minus x to the 3rd over 2 factorial plus x to the 5th over 4 factorial minus x to the 7th over 6 factorial, and there I am. So that's the 7th order Taylor polynomial, also known as the 7th degree Taylor polynomial. But you notice that it's not the first 7 terms of the Taylor polynomial because all of those in-between terms are all 0. So if you're going for non-zero terms, you would have to keep going beyond that. All right, in the last section, we're going to take this. We're going to find a few more Taylor polynomials, and then we're going to look at a couple of numerical cases.